Hello everyone, this is a video lecture for Calculus 1 section 6.4, the four-letter word, work. Work equals force times distance. That's your formula for the day. If you want to make it more intricate, you could say integral of your force dx, x being your distance. There you go. I don't know of any other formulas that we can generalize because there's a whole ton of specifics when it comes to individual problems. This is a pretty hard section, I'd say. It's pretty difficult. Lots of little things going on. A lot of word problems, too. And a lot of words, so I'm just going to do the best I can with this. It says, find the work done to lift a 210 kilogram object a height of 7 meters. And they say use the 9.8 meters per second squared for gravity. This one's very simple. So we have our kilograms times the 9.8, and that's going to be your force. And then your distance is the 7. Force times distance. So this is in newtons now, I believe. This is in meters. So when you multiply it, you get 1440 joules. Is that not newtons? Pretty sure that was newtons. They say joules, but I thought it'd be newton meters. Maybe they're the same thing. Newton meters, joules. 6.4.006. I mean, I could do the math side. You want the physics? You go see Dr. Ravani. So, midpoint rule. They say use 4 rectangles, and they have a ton of numbers. And if you haven't noticed any since now, about my drawings, I guess, my handwriting, my the tablet thing that I'm using, that it does not do decimal points very well, and that is the only fault with this thing. I love this tablet thing that I have, but it is not got a lot of great sensitivity when it comes to these decimal points. So it's kind of doing a pretty good job right now, though, compared to other times. Okay. Whew. Yeah. So midpoint rule, 4 rectangles. There you go. Midpoint rule says use these guys. I mean, we had a problem like this just last time. And so the 5.4 plus the 8.7 plus the 8.3 plus the 5.5, that's a point. And then times the width. The width between each of these guys is an 8 width, or distance, or whatever. And 223.2, they say joules. Again, that's fine. I'll take it. 64009. See, I can't do that decimal point. Suppose we have a 2 joules of work to stretch a spring from its natural length of 34 centimeters to 49 centimeters, period. Okay, so let's start with that. And then part A says how much to do this and that. Well, let me go ahead and give you some formulas, okay? So work is equal to the integral of kx dx. And I believe this is a variation of Hooke's law. Let me go ahead and write that up here. Oops. Hooke's law, which is F equals Kx. And so we got our force in there. To integral of force is going to be work and all that stuff. Well, where did that 0.15 come from, right? Well, it's actually from right here. That's 15 centimeters, or rather 0.15 meters. And that's going to be the important thing, is that we need to convert to meters. I don't know if the problem itself says that. I'm happy to tell you, hey, go ahead and convert to meters. So there you go. And it makes everything so much better. Well, your work for this was going to end up being a 2. And so we need to integrate this thing. It's not that hard to integrate. Oops, wrong way there. The 0 obviously will cancel, so you can plug this guy in. Now, I was going to do a fraction, but it just didn't work out that well. That's going to end up being a 4, and then we're going to divide. So 4 divided by 0.15 squared. Do I have an answer? I do. It's going to be 1600 over 9. Just keep it that way. It's fine. All right, so there's my K. This is my spring constant, I guess. So part A, it says how much work to go from 36 to 44. Remember that the natural length was 34, but it's saying 36 here. So really, I'm going 34 to 36, which is a 0.02 meters. And then I'm going 34 to 44, which is a 0.10 meters. Okay, and so then I'm going to do integral for my work. 0.02, 0.10 of my K, which I've already found, x dx. And you know how to do that one. All we need to do right now is plug it in. And I got 0.85333 joules. Okay. And then finally, part B, it says, how far beyond the natural length will a force of 45 newtons stretch it? Now, this is interesting. 45 newtons is a force. And they're wanting to know, what is x equal to? How much is it going to be stretched out? Well, F equals kx. That's Hooke's law, which I had mentioned. Move all that stuff over, solve for x. Not too bad. 0.2531 meters. The problem is that on this problem, they want it in centimeters. So you're going to have to convert it back into centimeters, although the only math possible on any of this is meters. I would say that's a pretty upsetting little thing, especially, let's just say, if that was on a test, that would be aggravating. So watch out. I'm just telling you now. And I don't make all the rules, so, you know. I do for Cal3, though. You can definitely, when you get to Cal3, you can tell me how wrong I am and tell me to change problems. I'm definitely willing to listen. But here in Cal1, I don't have the power to do that. Natural length of 22 centimeters, and it's going to be stretched to 32 centimeters. And why do I have a work? Oh, yeah. I see. It says, what's the work to do that? And that's kind of weird because it's very vague. And so 0 from the natural length. Notice that we're going 10. So 10 centimeters is 0.1 meters. And then kx dx. And we already have done this before. 0 to 0.10. Plug it in. Okay. Cool. That's your answer. Yeah, I know. It's just weird. There you go. They didn't change K. They didn't give me K, so. Okay. More springs. 64012. I have 5.4 joules of work to stretch a spring from 11 centimeters to 17 centimeters. 9 joules of work to stretch it from 17 centimeters to 23 centimeters. What is the natural length? You know what's so funny about this? Just okay, let's pause. Let's just say we're doing engineering, right? Engineering majors and all that. I'm totally down with it. This is cool. So we take these measurements of the spring, right? And they're saying, hey, what's the natural length of the spring? Well, you know what? All you have to do to find this is you just let the spring go. You just let it sit there on the table by itself. You don't touch it. Just take the spring out of whatever gadget it's in, set it on the table, and get a ruler. I'm not kidding you. That's how you find the natural length. You're not going to like this problem. You're not. And that's why I wanted to mention how easy it is in real life to be able to do this. Because what we're going to have to do is, of course, we're always converting. So we got 11 and 17, but both of those are going to be minus L. L being your natural length. Okay, and yeah, we know how to do integrals around here. We're integral masters at this point, right? Yeah. Okay. And so then we do all our math, and yeah, you get, guess what? We get a k over 2 times 0.17 minus L all squared minus 0.11 minus L all squared. And that's that. And so then we do the same thing for 9 is equal to 0.17 minus L to 0.23 minus L. I'm not going to redo all the math, but you can see right here that it'll be just the same thing, just with slightly different numbers. Cool. Okay, so essentially here we got 5.4 is equal to this, and 9 is equal to that. So we got this, we got that, and solve for L. So this is how I'm going to do it. It's for reals. I'm going to take all this, divide it to the other side, and solve for k over 2. Okay? And I almost don't even want to write this because it's just so long and arduous. But there is not a better way to do it. So there's that. I'm going to take this k over 2 business. I'm going to plug it in. So really we have 9 equal to 5.4 over all the stuff. And then times all this other stuff. When you started this video up, did you know? Did you know we would do this? So it's kind of a funny little comparison thing. I'm going to bring that up, pull this back down. So 9 over 4.5 is equal to this silliness here. I like how it's mathematical. You know, I'm looking at this thing and I see, I guess what you would call patterns perhaps, but just some kind of relationship between these things. And now we need to solve for L. So, all right. I'm going to be honest with you. I've got a whole 2 pages for this or something. It's not fun. So what you do is you FOIL out each one of these. You combine like terms, which honestly does simplify it significantly. And blah, 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 all that math, and eventually you get 5. Yeah, it's not even a decimal. Well, I mean, the answer is 0.05, of course, and then you got to convert it. But that's just funny to me. It's just so funny and sad. So I will recommend, if you're wanting to do this by hand, then you can go and do this and that and this and that and all of fun stuff. Do that. So there's also abilities to do this in calculators, let's say, and I'm not going to go through the specifics there, but at this point in the class, you should be allowed to do something like that. Next question. 64007. So we have a bucket, and it's 3 pounds. And there's a 50-foot deep well that it's going to be dunked into. It's going to carry 42 pounds of water up, but the bucket leaks at 0.25 pounds per second. That's a leaky bucket. Another thing is that the rate to come up the rope is 2.5 feet per second, and so then find the work done. This is a real legitimate problem here, guys. Leaky buckets are a very important engineering problem. Well, I mean, honestly, even with or without a leak, let's just say it is actually a very important problem. I would almost say maybe a bit too much for the scope of this class, but I don't make the rules. I just show up to work every day and teach, and then I go home and answer emails. So they have a Riemann sum of all things, because, you know, that's definitely what all the engineers were thinking out there. I got you, bro. So, oh my goodness. Okay. Yeah, this is wonderful here. So this is a lot of boxes to fill in, and this is just me great fun. I actually, all I did here, I'm just going to go ahead and tell you, I just found the formula. And you know how I found that formula? Just guess. I'm going to let you guess. Here we go. Yeah, I got it wrong 3 or 5 times. I got it wrong, got it wrong. I saw what they had, and I'm like, ah, now I see what's going on. So let me go ahead and give you what I did so that you can understand the specifics. Now, I actually did not do this problem in my notes. I didn't. And I know what I did. I did this. I just went and looked up what they had, and then I just copied and pasted it. I don't want it to be wrong or rude, but honestly, I'm stuck. Now, going backwards, seeing what the answer is, being told what to do here and there, yeah, that'll help. That'll help. And then I went and actually did the math eventually, and I got this guy for my final answer. There you go. So what's really going on here, right? I'm going to use a different color here. Notice that we have a 3-pound bucket plus 42 pounds. This is all pounds, right? That's where the water, but then it's leaking, right? It's leaking. Now, if it were leaking 0, I wouldn't even talk about any of this. But instead, it's leaking to 2.5 per second, basically, okay? So where does that 50 come from and all that stuff? Well, for the well, basically here out of these guys, we got our rate here, and then with our feet. No, I'm sorry. This one. This is our rate here and our feet. If you mush these together, what you end up with is seconds. So this actually yields seconds. And then this one here is a per second. This is pounds per second. And so you're saying pounds per second multiplied by seconds, and they both cancel, leaving pounds. Pounds minus pounds. 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 Well, that's foot pounds because they're talking about integrating all that stuff. But on the inside here, you got pounds. That's your force, isn't it? Force, pounds, same thing. It is actually. So there's a lot behind it. You know what to do. 64023. So there, I drew a really nice picture here on my notes. It's like, I don't know if I even did it because it's so nice. I know I did it, but I mean, it just looks so good, and I'm going to just junk it up here in front of you. I blame it on my tablet. So we got 15 meters here. We got 4 meters here, and there's a spigot that's coming out of this thing. Oh, there's a spigot that's coming out of this thing that is an additional 3 meters high. Not to scale or anything. Okay, so I'm trying to pump water out of this thing. Oh, this is 4 meters. Oh, man. Why do I have that? I don't know. Okay, well, there you go. So, there's water in this trough thing, and I'm pumping it out, and it takes force to do that. So it says the tank is full of water. Find the work to pump it out of the spout. Remember that gravity is 9.8 meters per second squared. Also remember that water is 1,000 kilograms per cubic meter. Okay. And so here's your formula. F is equal to MA. Have you seen that one before? Surely you have. It's very, very basic force formula. And so here we go. I'm going to try my hardest. I got 1,000 for my density, and that is in the units of kilograms per meter cubed. And then I'm going to multiply it by the width, which is in the form of meters. And then I'm going to multiply that by the length, which is in meters. And then I'm going to multiply that by the height, which is in meters. And then I'm going to multiply that by the 9.8 meters per second squared, because, well, that's the A part. And so we got to figure out what we're going to be doing here. I am not sure exactly how they reason this, but I know there's some way that they tell you within the problem, but that the width of this here is equal to its height. Okay, so however high you are is also how wide it is. Oh yeah, I know exactly why. Right here, 4 meters across, 4 meters high. Yep, that's how you know. Okay, cool. So then if you're up here at 3, then it must be 3. So there you go. We can use a single variable. I used y for all that. So basically here on my huge formula, I just replace these with y's. Also note that meters cubed, 1, 2, 3, leaving kilograms. And so kilograms times this stuff is, so that's mass, by the way, not meters. So mass times acceleration, there's your mass, there's your acceleration, here's your force, and you're done. Yay. Well, I did all this math, of course, and I got 147,000 y squared newtons. Turn the page. Well, it seems that they want the work done. And so I'm going to say integral of my force dx dy. Okay, that's better. Cool. So I'm going to ask what are the limits? Well, you already know they're going to be 0 to 4, and that makes sense. But the problem is that I need to get 3 feet higher. I did not spell higher correctly. I need to get 3 feet higher. 0 to 4. That's as much as I'm pumping out of here is going to be all this, right? But how do I get it 3 feet higher? How do I do that? Well, let me tell you what the real formula is going to end up being. And then I'll explain it to you because that's what I'm doing. 147,000 y 7 minus y dy. And this should equal the answer 5,096,000 joules. Okay, awesome. What just happened? Formula here was y squared. Well, that was actually incorrect. Because this was 1y, and this should have been a y to make the y squared. So I was incorrect a little bit here. The reasoning is that my height is related to the y, but I need to start at the 7 and go down. And so if you plug in a 0, you're pumping out all 7 meters. Well, I'd say start with a 4, actually. Start with a 4, and then you go to the 0. And that works. So if you want to just say, oh, well, that works, well, then that works, and you're done. But I actually have a goodly chunk here in my notes about why. Why does that work? Let's just say that y equals 0, just for a second here. What does that even mean? And so I'm going to have 0... well, yeah, let me do the formula, I guess. So I got that much times 0 times 7 minus 0 is equal to 0 newtons of force. So that's kind of odd, 0, and I'm getting 0 newtons of force. Let's try other ones. So 14000, 1, 7 minus 1. I did the work here, and 147,000 newtons. That's also a 1 right there. Why did I... No. Why did I have a 6 there? Why do I have a 6 there? That should be a 0. I don't know why I did that. 6. That's not my point. Let's just ignore that. And you're like, what is going on? Just hold on. I'll explain it. Just hold on, okay? What if I plugged in a 4? What if I plugged in a 4? Okay? So I do all this. 1764000 newtons. Okay. What's going on here? Well, let's draw some triangles. If I'm going from 0 to 4, so then am I doing 0 way down here, 0 height? And then 4 height, it's filled, isn't it? 4 height, 0 to 4. Well, kinda. What I'm really doing is going from 4 down to 0, because I'm starting with a full tank, and then I'm pumping it out. And so the 4 amount, notice that I have the 4 depth, height, whatever you want to call it, but then, or no, width, I'm sorry, that's width right there. That's width. But then this is my height that I'm trying to pump it out. How much higher do I need to pump it? 3 extra feet. Okay. But like, let's just say that we're way down here and we're calling it a 1 height right now. So my y is equal to 1. And then, you know, I got my little spigot thing. So how much am I actually pumping out here? That's probably where that 6 came from. 6. Like this was 6. My notes were a little bit off. Oh well. So that is 6. I'm trying to pump out 6 height out of it, but I don't have very much to pump. And so, anyways, blah, blah, blah. I think it's making sense. I told you the formula. Now you know what to do on that problem. 64004. I've got the work is in foot-pounds. Okay. It says we have a constant force of 85 pounds. Pause for a second. Force in English Standard Version stuff is English something, I don't know. Blah, blah, blah. The English Standard Measurements is it's pounds. Force is pounds. That's not the case in the metric system, where force is in newtons, kilograms is mass. So what is the English version of mass? It's actually called slugs. Yeah, it's actually called slugs. But we don't ever use it, so just ignore it. Basically, pounds already has gravity attached to it, unlike kilograms, which does not have gravity attached to it. Here on Earth, you're the same kilograms as you are on the moon. So if you were on the moon or on Earth, you have the same kilograms, but you would have different pounds. Okay? Blah, blah, blah. All right, so you're pulling a cart 220 feet, and they say, what's the work done? Okay. Well, I don't know why I put another 0 in there. Give me a second. I mean, I must have been half sleeping during all this. I got the right answer. So, yeah, it's just my notes here. Hold on, I'm going to get myself a pencil and correct this thing right quick. I know, it's so rude to do this during the recording. Well, wouldn't you want it to be fixed? That's supposed to be a 1. All right, and that's not supposed to be there at all. It's okay. Moving on. 220, multiply it by the 85, and you get 18700 foot-pounds. Why did I multiply them? Because you had feet, you had pounds, you multiply them to get foot-pounds. Wow! Isn't that just the coolest thing? So we're done, and I hope that you're seeing one thing from this experience, that every one of these problems is a little different, and my goal here today was to just show you how to get started on a lot of them, what to expect, and honestly, I'm going to tell you, if you don't know what to do, just get it wrong a couple times. See what their format is, see what their answers are. It might help you. Okay, thank you very much, and have a great day.